Lab 5 is measuring BglB activity so that we can determine certain characteristic kinetic parameters. And we want to compare these parameters between the wild-type enzyme and the mutant that we've designed. The overall objective is to understand the structure-function relationship for BglB and enzymes in general. Before we can do that, let's step back a little into labs 3 and 4, where we chose an amino acid to mutate in the first place. All right, here's BglB as visualized using Foldit. And we spent labs 3 and 4 going over Foldit, so I'm not going to go through that now. But what I want to do is I want to hone in on the active site, okay? And we can see in the middle here is the substrate, okay? So that defines the active site for us. All right, so let me spin this a little bit, and I want to take a look at the active site from behind. All right, so now I'm spinning everything around. Be careful where you click, right? And what I notice is here, once again, here's the substrate. Now remember, BglB cleaves beta-glycosidic linkages. All right, so this is a beta-glycan. All right, and I think it's just a disaccharide connected by a beta-glycosidic linkage. All right, so you can see near that substrate is this amino acid tryptophan. Okay, now I've highlighted it. It's highlighted in pink. Let me spin a little bit more to get a little bit of a different look at it. Okay, and you can see that it is in close proximity to the substrate. Although what you don't see is you don't see any interactions. You don't see any hydrogen bonds. Tryptophan doesn't really have any functional groups available for hydrogen bonding. There could be something like a hydrophobic interaction. Tryptophan is hydrophobic, but this disaccharide substrate is not hydrophobic. So I'm not really expecting a hydrophobic interaction either. I could be mistaken. So that raises a question, what is this particular tryptophan doing in the active site? And actually, before I go any further, let's get some information on that tryptophan. I know it's tryptophan. I recognize the side chain, and so should you. But let's get more information on it. And here it is, tryptophan 409. All right, and note that arrow goes to the part of the amino acid that's the peptide backbone, and then the side chain is sticking off of there. And like I say, it's in close proximity to the substrate. Can't really say if or how it's interacting with the substrate. And to me, that's what makes it interesting. All right, so this is an amino acid that I want to mutate. All right, so the question is, to what do I mutate it? All right, so let's think about that for a while. And let's use our nomenclature. So remember that we're dealing with tryptophan 409. So tryptophan 409 will be abbreviated this way. And then I want to decide what to mutate it to. Now I can make a conservative substitution. I can make a very different substitution, or I could do something in between. All right, so I think the most conservative substitution you can make in this case is to phenylalanine. Okay, phenylalanine is also an aromatic ring, although tryptophan has the double ring structure. Phenylalanine doesn't have that, but it is otherwise a hydrophobic amino acid like tryptophan. Another substitution you could make is W409Y. Okay, so mutate that tryptophan to tyrosine. Tyrosine's like phenylalanine, except that it has a hydroxyl group. All right, so now we're adding a little bit of hydrophilic nature to this amino acid that is otherwise hydrophobic. So that could tell us something about the nature of the interaction with the substrate, if any. Or we could do something a little bit crazier, right? We could make change it to a very different amino acid, like aspartic acid or glutamic acid. Okay, so that's a D. And that would dramatically alter the nature of that amino acid, and who knows what it would do to the structure and activity of this enzyme. I mean, so there's a lot of different things we can do depending on just what we want to find out. And then finally, we could make something that I would call a more of a neutral substitution and change it to alanine. Okay, so alanine is a simple amino acid, not the simplest amino acid. Glycine is the simplest. But I think changing it to alanine would kind of have the effect of just removing that tryptophan side chain and not having anything there. All right, so that would allow us to ask, is the tryptophan important at all? Before we get into, exactly why it's important. So I think for my money, that's what I'm going to do. I'm going to go with the alanine substitution. All right, so, and remember how to make the substitution. Again, we've done all this before, but note the energy score there. And now that I have tryptophan highlighted, I'm going to go ahead and call up the mutation window, and I'm going to select alanine. Okay, and there it is. So there you see alanine substituted where tryptophan was. Okay, so here we see the two different proteins, and I've zoomed in. I've zoomed in on the active site. There's the substrate once again, and here it is again. And this is the original protein. So remember, this tryptophan here was the original amino acid. Right, and that's just a side chain that I've circled. And here is alanine that I've changed it to, and that's a tiny side chain. All right, and you can see, so this substrate is much more exposed now with the alanine substitution. Okay, so just to review some of the Lab 4 material. So once we make that substitution, we want to look at the change in energy state of the whole protein. And I've done that. And then I've gone through the optimization, the wiggle and shake. Okay, and we can see this was the original energy score. Okay, that REU is Rosetta energy units, or you can think of it as relative energy units. And you can see that it's gone up a little bit with the alanine substitution. Okay, so this is the alanine substitution, W409A. And you can see that it's gone up by 4 energy units, 4.161 energy units. Okay, so and that puts it in the iffy range, right? So remember, energy change of +2 is probably good if certain other parameters are met. An energy change between 2 and 5 is iffy. Between 5 and 10 is very iffy, and then beyond 10 is probably not workable. So this qualifies as iffy. I think I'm going to go with it. I'm going to try for it. And I also looked at the local energy score, and you can see there's a small increase in the local energy score, nothing that concerned me. And the clashing is within acceptable parameters. So all in all, I think we can go ahead with this mutation. Okay, and if you'll recall, the rest of Lab 4 was about designing an oligonucleotide to introduce this mutation into BglB. I'm not going to review that here. I'll refer you to the Lab 4 video. All right, so we've selected an amino acid to mutate, and we've decided what to mutate it to. And presumably at this point, you've also designed an oligonucleotide to generate that mutation. So that brings us really into Lab 5 proper, and Lab 5 is measuring beta-glucosidase activity. All right, so let's recall that beta-glucosidase B is an enzyme. It's a glucoside hydrolase. All right, it's a beta-glucoside hydrolase. That is, it cleaves beta-glycosidic bonds. All right, and of course, the best example of a beta-glycosidic bond is cellulose and cellobiose. Those are substrates for this enzyme. That is, bacteria use this enzyme to digest cellulose. All right, so in the laboratory, we're not going to use cellulose. We're going to use this reagent here, okay? Paranitrophenyl D-beta-glucopyranoside. Now, that's a big word, so let's break it down a little bit. First of all, the nitrophenyl group, paranitrophenol, okay? So this is phenol. Without the nitro group, it would be phenol here. And it has a para-nitro group. Para means that it's opposite the phenol group. All right, so that's going to turn out to be very handy. All right, so let's keep that in mind. That's going to turn out to be very handy. And the rest of it is glucose, okay? D-glucose, as the glucose that's used generally. And it's a beta-glucopyranoside. Okay, so this is a beta linkage. I've drawn through it here, but I hope from this diagram you can appreciate that this is a beta-glycosidic linkage. Here's another view of the substrate right here. This is also paranitrophenyl glucopyranoside. And hopefully from this view, you can see very clearly that this is indeed a beta-glycosidic linkage. All right, and beta-glucosidase, B, cleaves that beta-glycosidic linkage, all right, to yield the products glucose and then this paranitrophenol. All right, and this turns out to be very handy, as I said before, because it's easily detected in the lab. All right, that's really what you need to know. It's something that we can very easily measure in the lab. All right, so how do we measure it easily in the lab? Well, a little bit more detail than we probably need, but this creature right here, this paranitrophenol, um, isomerizes between two forms, a protonated and deprotonated form, and this deprotonated form absorbs strongly at 410 nanometers. All right, so we're going to put it in a spectrophotometer, and we're going to measure absorbance at 410 nanometers. All right, so what the light that's not being absorbed is being reflected or transmitted, and that turns out to be yellow light. So this compound is yellow to our eyes. But in the spectrophotometer, we're going to measure it at 410 nanometers. Actually, I think the protocol says 420 nanometers. Okay, so something very close. But the point is we can use this substrate. So this is going to be the substrate for our enzyme. We're going to make our mutant enzyme, and we're going to compare it to wild type. So we're going to have two, wild type enzyme, mutant enzyme, beta glucosidase B, beta glucosidase B. And we're going to measure its activity, and we're going to measure its activity against this substrate. And that way we can compare the activity of the wild type enzyme as well as the mutant that we've made. All right, so we can measure the activity of the enzyme in the lab, all right, using that reagent, glucose paranitrophenol, paranitrophenyl glucose. And when we do that, the readout is going to look something like this. Okay, so on the x-axis is time, so we're going to look over a period of time, and on the y-axis the amount of product formed. But remember, this product absorbs strongly at 420 nanometers. So what we're really measuring is the absorbance at 420 nanometers. But that's a stand-in for the product form. All right, and so this line, it's very nice and linear initially, right? And then it starts to taper off a little bit. All right, so and it is this part down here that we're interested in, the linear part. That's usually called V or sometimes V0, as in the initial velocity of the reaction. And note that it does taper off over time. This is inevitable because as the reaction proceeds, you're using up substrate. And when substrate becomes limiting, the reaction slows down. Also, you're building up product, right? And as product accumulates, it could have an inhibitory effect on the enzyme. All right, so this tapering off is inevitable. And what we're really interested in is what happens down here in the linear portion. And so remember, this line can be represented with a slope. Very important to keep that in mind because the slope is what's going to be reported back to you in terms of the raw data. All right, so the raw data we're going to get from this experiment is the slope. All right, and of course, technically, that is the change in absorbance of 420 nanometers over time. But that can very easily be converted into an amount of product over time. Okay, so we're measuring enzymatic activity as the amount of product formed per unit time. All right, and then we can take that a step further and measure specific activity by correcting for the amount of protein that's in the assay. All right, so so we can get that V0 measurement, or we can get the reaction velocity, and we can measure that reaction velocity at different substrate concentrations. All right, so that's what this plot is down here. Okay, so this approach is called Michaelis-Menten kinetics, and the plots that we get out of it are called Michaelis-Menten plots. And as part of your lab report, you're going to be making these Michaelis-Menten plots. All right, and so what they are is they're varying the amount of substrate. All right, and then you're measuring that V0 once again at different substrate concentrations. And what you typically get is a curve like this. All right, and so what happens once what happens is that this velocity increases at low substrate concentration. The velocity increases rapidly, but then as you get to higher and higher substrate concentration, velocity increases less rapidly and eventually flattens out altogether. Okay, so this is Vmax. That is the maximum that the maximum rate at which the reaction can proceed. All right, and physically, you should think of this as saturation of the enzyme. Okay, so Vmax equals saturation of the enzyme. That is, you have some enzyme present, it's catalyzing the reaction, making it go faster. And as you add more substrate, you're occupying more of that enzyme, and so more of that substrate is going to be converted, and so forth, until you get to a point where you've filled up that enzyme completely with substrate, and then adding more substrate doesn't make any difference, okay? So Vmax represents saturation of the enzyme. Another key parameter that we can get out of this is the Km. All right, and Km has actually a technical definition. All right, so Km is the concentration of substrate. Okay, so substrate concentration that gives half maximal velocity. All right, the substrate concentration that leads to 1/2 Vmax. Okay, and if I can just get a little pedantic here with you for a moment. Km, this is a capital K and a subscript capital M, as in Michaelis, the Michaelis constant. All right, so capital K, subscript capital M. Sometimes it's not written that way because we're limited by the word processing program we're using. So sometimes it'll just be capital K with the lowercase m. But this is the proper way to write it. So here it is right here, capital K with the lowercase m. That's because the text editing abilities on this graphic is limited. All right, but here it is visually. All right, so here's Vmax. This is half Vmax. All right, so I find out what half Vmax is, and then I draw a horizontal line over to the graph, and then I drop a vertical from there, and that's going to give me a substrate concentration, right? Because along the x-axis is substrate concentration. Okay, so once again, Km is the substrate concentration that gives 1/2 Vmax. That's the technical definition. What you can think about it is you can think of it as a measure of the affinity of the enzyme for the substrate. All right, so the lower the Km, the greater the affinity. All right, so the lower the concentration that gives you half maximal velocity, the greater the affinity of the enzyme for that substrate. And of course, the higher the Km, the lower the affinity. All right, now let's look at this graph over here, which is also a Michaelis-Menten plot. It's actually 3 Michaelis-Menten plots put on top of one another. And so this 0 represents the original graph. Plus means we've added more enzyme, so we've increased the amount of enzyme. And minus means that we've decreased the amount of enzyme. All right, so if with more enzyme present, the reaction to Vmax is going to be higher, right? The more enzyme that's present, the more substrate you're going to need to saturate the enzyme. All right, so, or I should say that the enzyme is going to saturate at a higher level and lead to a higher Vmax. And of course, if you have less enzyme, that's going to lead to a lower Vmax. Less enzyme means that the enzyme is going to saturate earlier. All right, so varying the amount of enzyme changes Vmax naturally, right? The more enzyme you have, the faster the reaction is going to go. However, it does not affect Km. The affinity of the enzyme for the substrate remains the same. Okay, and you can see why that happens. So half Vmax is going to be different each time, but the shape of each of these curves is also going to be different. So it's going to land you at the same Km. All right, we can formalize the relationship between reaction rate or reaction velocity and substrate concentration mathematically in what's known as the Michaelis-Menten equations. Okay, so that's Michaelis-Menten equation, and it's written right here. And what it says is the reaction rate, or V0, is equal to Vmax times substrate concentration divided by substrate concentration plus Km. Okay, so this is a little bit complicated, but let's take some simple examples. All right, let's take the example where the substrate concentration is low compared to Km. Okay, if substrate concentration is low compared to Km, this term kind of goes away, all right, and this equation reduces, all right, so then the equation becomes Vmax over Km times substrate concentration, all right, and so the simple way to think about this is that at low substrate concentration, the reaction rate, or V, is proportional to the substrate concentration. And that's exactly what you see in those curves on the previous slide. The reaction rate is proportional to substrate concentration at low substrate concentrations. Okay, so that's one simple case. Now let's take another case where substrate concentration is high compared to Km. All right, so if the substrate concentration is high compared to Km, then this term kind of goes away. and this just becomes S over S or 1. All right, so V is equal to V max. So, and that's exactly what V max is. The maximal reaction rate you reach when you have saturating levels of substrate. All right, and then finally, perhaps the simplest case of all, what if the substrate concentration is equal to Km? Well, then this just becomes S over 2S, which is 1/2. All right, so then reaction rate becomes 1/2 V max. And once again, that's the simple definition of Km, the concentration of substrate that gives 1/2 V max. All right, so I've gone through the Michaelis-Menten kinetics rather quickly, but be aware that this stuff is all explained in your lab handout, so I strongly recommend that you read that lab handout very carefully. There are also references within the lab handout where you can learn more. And then finally, I want to talk about this. Okay, specific activity. In the end, that's what I want us to measure, specific activity. So, and that is the micromoles of product, and in this case, the product is paranitrophenol, per minute per micromole of protein. Okay, so if we deal with just the first part of this equation, per minute, that's the reaction rate, the amount of product formed per minute. Okay, simple enough. And then this just goes a little bit further and corrects for the amount of enzyme that is in the assay. All right, so micromoles product formed per minute per micromole of protein. That is the parameter that we're going to be measuring. We're going to measure, the raw data is going to be, once again, slope, which is change in absorbance, but we're going to convert that to a specific activity. Okay, so I've given you some background on kinetics, and I've given you some background on the assay that we're going to use to measure BglB activity. But now we have to talk about how we get the raw data and analyze it. First, of course, we have to talk about getting the raw data. And of course, we're not in the lab this semester. So if we were in the lab, you'd be making your mutations, and then you'd be measuring enzymatic activity right in your own lab. We can't do that, so we have to rely on data that others have generated. Okay, we're going to use their raw data and do our own analysis. And so where do you get that raw data? Well, you can probably figure by the fact that you're looking at a Canvas page that there are links on the Canvas page that will take you there. All right, so okay, so this is the link to the lab handout. This is a link to the D2D, Design to Data website. You know, that is the umbrella organization that is crowdsourcing this investigation of BglB. So there's a lot of data on that website, and I'll go there in a moment. These two videos, of course, are Susie's videos, and it goes into more background and detail about the BglB assay. So watch that if you want. And let's just use my data analysis, all right? I would not use Susie's data analysis because what I do is a little bit different. And I actually make it much simpler for you. Okay, so, and these, of course, the lab 5 questions, which you've already done. All right, so this is a link to the data that's part of the D2D project. So let's click there. Let's open up that one. And then the other one I want to open up is the example spreadsheet. Spreadsheet that I've made that you can use to analyze your data. Okay, so let's go to the public website and see what's available there. Okay, so what we have here is a long table with a lot of enzymatic activity results. Okay, you can see that top line says wild type. Okay, so that is the unmutated, the native BglB. And then below that, you have all the mutations that have been analyzed or are scheduled to be analyzed. Okay, they haven't all been analyzed yet. And note that they're in order. Okay, starting with the amino terminus. It doesn't start with amino acid 1, but it starts with amino acid number 11, 12, and so forth, and so on down the line. And remember, the mutation that I was interested in, or the site that I was interested in, is W409, that tryptophan at position 409. Okay, so and let's look at what we have here. We have W409. So other people think that's an interesting amino acid also. All right, so that's good. There's W409D. which is one of the things I suggested, but I decided against. There's W409Y too, another one that I suggested, but decided against. There is no W409A, okay, the alanine substitution. The closest thing they have is W409G. Now, we've been told not to use G, but in fact, G will work in some situations. All right, so I think since the mutation that I want to analyze is not here, I'm going to settle on the next best thing, W409G. All right, so that leaves open the question, what mutant should you analyze? All right, and I've kind of answered that question for you once again on this separate spreadsheet. All right, so the first thing that it says up here is which mutant to analyze. Okay, so you've settled on a mutant to analyze in lab 4. If that mutant has been analyzed in the data set, go ahead and do it on your own. Go ahead and do your own analysis also. Okay, so if it happens to be in the data set, great, use it. If your mutant of choice has not been analyzed as part of the public project, then choose something similar. Okay, so in my case, I got kind of lucky. They didn't have W409A, but they had W409G. It's the next best thing. So hopefully you can come up with something similar to that. So if there's another substitution at your site of interest, then go ahead and analyze that, even if it's a different amino acid. Okay, if not, then choose something nearby. Look for a nearby amino acid that has been mutated. All right, but the point is that you're limited. I know you've already handed in lab 4 and you've designed your oligo, so we're not going to change that, but we can change which data set you analyze. All right, so choose an amino acid as close as possible to the amino acid that you've chosen. All right, and just take whatever mutations they have there. And that's really the best you can do. All right, so but the point is you have to get some raw data and you have to analyze it. Okay, so look this over when you get a chance. But now let's go back to the data. All right, so this W409G, and I've lost it here. W409G right there. All right, and so some of these actually have links. A lot of them have numbers, and a subset of those that have these parameters calculated also have links. All right, but the links are hidden. So, and this is something you'll never see in the instructions. So in order to uncover the links, you have to press this top link. All right, and now it's going to reload the page, and a lot of things are going to have links to it. All right, so now let's go back down. See, some of them have links to the raw data. Some of them have obviously been done because they have parameters next to them, but there's no link to the raw data. All right, so we want one with the link to the raw data. And once again, as you might guess, W409G is available. Okay, W409G, there is a link to the raw data. So I'm going to click on that, and it's going to take me to the raw data. And what is the raw data? But once again, it's a slope, right? As I've already explained to you, the raw data you get back is a slope. The change in absorbance at 420 nanometers per minute. All right, so step 1 is going to be to convert that absorbance into an amount of paranitrophenol, into a micromole amount of paranitrophenol. Okay, so but before I get into that, I want to show you a few other things here. Okay, so that's the slope. And this is the mutant, W409G. Now, every time a mutant is analyzed, it's analyzed in parallel with the wild type enzyme. Okay, so to go along with this mutant analysis, there's also analysis of the wild type done in exactly the same way. Okay, note that we're varying substrate concentration, right? Michaelis-Menten kinetics asks us to vary enzyme substrate concentrations and look at the reaction velocity at each different substrate concentration. So here are the substrate concentrations. And remember, the substrate is paranitrophenyl glucose. All right, and here are their concentrations: 0.02 millimolar, 0.07 millimolar, 0.29. I don't know how they settled on these numbers, up to 75 millimolar. Okay, and that's going to be the same in the mutant case as it is in the wild type case. And then each enzyme is done in triplicate. Okay, so 1, 2, 3 measurements at each substrate concentration. Something went wrong here, so there's a little bit of data missing. That's okay. It's not really going to affect us too much. All right, so that's true also of the wild type. Okay, varying substrate concentrations, and at each substrate concentration, the activity is measured in triplicate. All right, so again, good science always requires replication. And then finally, there's information on the amount of protein that went into the assay. All right, so every time you make a new mutation, that's essentially a new protein, right? And it's going to go. You're going to purify that protein from a bacterial source. All right, so we're doing this uh, enzyme activity assay on purified protein. And that purification is going to come out a little bit different every time. And of course, it's going to be different between the mutant and the wild type. All right, so we need to know how much protein we're using in the wild type in the mutant reaction and how much protein we're using in the wild type reaction. Okay, so once again, these data are slopes, and this is the data that we're going to use for analysis. All right, and like I said, I've made it kind of easy for you because I've prepared this spreadsheet. All right, and there's a lot of things on this spreadsheet, but first of all, there's a table that looks a lot like the table from the raw data page. All right, and I'm just gonna, this says up here W409G versus wild type. I'm just gonna do the mutant, and I'm gonna leave it up to you to do the wild type analysis. Of course, you're not gonna use this mutation. You can't use W409G. You have to find a mutation of your own to analyze. But note how I have this table set up. I have the varying substrate concentrations, and then I have a place for the slopes in the 3 different trials. Okay, so this first table, these data are directly from the D2D website. So I'm just going to copy and paste. Except that it's not that easy to copy and paste. There's a little bit of a problem when you copy and paste. So let me just copy all this. Okay, copy, Command C. And rather than paste it right in here, because I know it always comes out wrong, I'm going to I have another page set up here, convert to usable text. So I'm going to click on that, and I'm going to paste those numbers in here. And I pasted it earlier, but let me start afresh. All right, so let me just pick a cell, and then I'm going to do Command V. And you see that it comes out, it's a little bit askew, and that's why we have to run it through this page first. So I'm going to take this data that's askew, and I'm going to fix it. Okay, so now we're all good to go. All right, so this A through H is a row number. All right, and once again, these are substrate concentrations, so these are the numbers that I want. So I can go ahead and copy and paste these numbers back into that original table. All right, so Command C, go back to that original tab, and I'll paste them in here. Okay, so far we haven't done anything. I mean, this got filled out, but so far we haven't done anything. And let me just change it a little bit. There's a better way to do it rather than just do Command V. I'm going to, that didn't work. Okay, so I'm losing the lines of the table, but that's okay. All right, so we haven't changed anything. These numbers here are exactly the same as these numbers here. Carried out to many decimal places. I don't know why so many. All right, so this is the raw data. And remember, that raw data is the slope of the absorbance, all right, the change in absorbance per minute. So what we want to do is we want to change this absorbance to micromoles of paranitrophenol, or micromoles of product. All right, and how do we do that? So once again, these tables kind of do it for you. So how are we going to do that? We're going to do that using Beer's law. Okay, so Beer's law, simply put, okay, so Beer's law, absorbance equals epsilon CL. Okay, so this is the molar absorptivity. So epsilon molar absorptivity. How much absorbance does 1 molar solution give? Absorptivity, or the molar extinction coefficient. Okay, C is concentration. That's the parameter that we're after, right? We want to know the concentration of the paranitrophenol. And of course, once we know that, if we know the concentration in the volume, we can convert that to an absolute amount of paranitrophenol. And that's going to be actually not in micromolar, but in molar. And then L is the path length. Again, this is explained in more detail in the handout. All right, so with all that in mind, let's look at this cell right here. So I'm clicking on that cell. And when I click on that cell, I get this equation. All right, it's showing me the equation. All right, so C17 is the raw data. Okay, so this cell corresponds to this cell. Okay, so this is C17 right there, right? So I'm going to start with that data. I'm going to start with that raw number, and then this is the molar extinction coefficient, right? So if I want to solve this for, if I want to solve that for concentration, all right. So to solve this for concentration, concentration equals the absorbance divided by the molar extinction coefficient and times the path length. All right, so that's what, we got to go back and forth a little bit here. That's what this is. So C17 is the number from that. Well, that's the absorbance, or the slope of the absorbance. And this is the molar extinction coefficient, or the molar absorptivity, 10,660. That's the path length, okay? So this is absorbance divided by molar absorptivity and the path length. All right, so this is absorbance. That's the molar absorptivity. That's the path length. All right, so that gives me the concentration, right? So that gives me the concentration. This is the volume, okay? So the assay is done in 100 microliters, okay? Microliters, 1/1,000,000th of a liter. 100 microliters is 100 millionths of a liter, or 10 to the -4th liter. All right, so that's the volume of the reaction. All right, so concentration times volume gives you the amount in moles. And then finally, I multiply by 10 to the 6th because I'm changing moles to micromoles. 1 mole is 10 to the 6th micromoles. All right, so when I do all of that, I get this very small number. All right, so you'll have to do it in your case. It's always going to come out differently. But that's what I wind up with here. All right, now there's one more step to go. Okay, so now I've started with an absorbance, the slope of the absorbance. Okay, so change in absorbance over time, and now I've changed that in the change to a change in micromoles of product per unit time. All right, so this was a change in absorbance per unit time. This is 0.0001 micromoles paranitrophenol per minute. All right, so I've changed that. So I've changed that from an absorbance to an absolute amount of paranitrophenol using the Beer's law. All right, there's one more step to go. Okay, so the final step, and once again, this is done for you in this table. The next step is to correct for the amount of protein in the assay. All right, so now I'm once again I'm starting with this change in paranitrophenol per minute. So that's cell C30, and I'm going to start with that cell C30, and I'm going to divide by the protein concentration. All right, so what is the protein concentration? Remember, we had these parameters here. It tells us how much the absorbance of the protein and the dilution factor. All right, so that's all here. This, once again, is the absorbance at 280 nanometers of the purified protein. This is the dilution factor. All right, and this is how we calculate the amount of enzyme used in the reaction. Okay, so it is once again, what we have here is the absorbance, 0.436, C10, 0.436. Let me write this down. It's the same as before. It's still Beer's law. Okay, so once again, we're starting with the absorbance, and that comes from cell C10. That's that cell right there. Dividing by the molar absorptivity, and in this case, multiplying by the dilution factor. All right, so we didn't put the enzyme directly in the spectrophotometer. We diluted it tenfold first. All right, so we have to multiply by the dilution factor. So make sure you're looking at that. And in this case, we also have to multiply by the divide by the path length. But in this case, the path length is 1 centimeter. Okay, so dividing by 1 doesn't make any difference. All right, and now this is the amount This is the amount of enzyme used. So that's 25 microliters. Okay, 25 microliters of enzyme is used in the assay. All right, so that's 25 microliters expressed as liters. And then finally, once again, we're multiplying by 1 million because we're changing moles of protein to micromoles of protein. All right. All right, so that's what's happening here. So now we're taking that change in the amount of paranitrophenol, and then we're just dividing by the amount of protein. Okay, and that's giving us the specific activity. All right, micromoles paranitrophenol per minute per micromole of protein. All right, and I'm calling it specific activity. What they're calling it here is K observed. Not exactly sure what they mean by K observed, but that's the reaction rate, the observed reaction rate, K observed. All right, and remember we've done that in triplicate. So we've done them at every substrate concentration. We've done it in triplicate. Now I have to be careful. Remember there was some data missing here, so I should delete that data point because that's gonna. If you delete a data point, it gets ignored in when calculating an average. All right. But if you put the 0 there where there should be no data, then that 0 is going to be included in calculating an average. So I should delete those. Now this is the master spreadsheet, so it's been deleted. I'll put it back in before you get to it. All right, so I've done the assays in triplicate. So now I can take the average of those and the standard deviation. All right, and then this is what you're going to plot. This is what's going to give you your Michaelis-Menten plot. The substrate, the specific activity or the K observed as a function of substrate concentration. All right, and that graph is going to come out like this. So once again, substrate concentration, substrate paranitrophenyl glucose, and then this is enzyme activity, micromoles paranitrophenol per minute per micromole protein. And you see you get kind of an, even if this activity overall is very low, but you still get this kind of nice Michaelis-Menten plot. All right, and then you can also include in there the standard deviations. It was done in triplicate, so we can calculate a standard deviation. That should be included on your graph. All right, so what else should be included? Okay, so then there's one last thing in this spreadsheet. What goes into your report? Okay, so we don't have a separate notebook for this particular lab. So I'm going to have you put some of this information into the appendix. So your report should include an appendix. All right. And that appendix should include a table of raw data. All right. So this is the raw data. All right. So that should be included in your report, not as part of the report proper, but in an appendix. And then the data analysis, this data analysis that leads to this number as a table should also be included in your report as, once again, as an appendix. I don't want to see all this data. I don't want to thumb through all this data as part of your report. All right, but then the analysis that does go into your report is a Michaelis-Menten plot for the wild type and the mutant enzyme. All right, so there should be 2 Michaelis-Menten plots. You can, I guess you could do it all in one plot, but I'm not sure. That would get kind of messy. Make sure it's properly formatted with a best fit line. All right, so using Google Sheets, I don't think it's too easy to put a best fit line there, but you can draw it by hand or there's various things you can do. But remember, for a proper Michaelis-Menten plot, we should have a best fit line. And then you should also include in there the visualization for calculation of Km and Vmax. Okay, so for Km, you're going to draw a horizontal line over to the y-axis and tell me what's the maximal velocity. And then you're going to find half Vmax and draw a line from there to the graph and then drop a perpendicular down to the x-axis and give me the concentration of substrate that gives half maximal velocity. All right, so those visualizations should be included in your plot. And then finally, you should have a table comparing Vmax and Km for mutant and wild type enzyme. Okay, so I said before that I've done a lot of it for you. This spreadsheet does a lot of the work for you. I'm going to delete everything from here, so it'll be clean and pristine when you get it. But this spreadsheet does a lot of the work for you, so make sure you understand it. And if you don't understand it, ask me a question.